So hello and welcome. Thank you for having me at this Furhat Conference. In the next 15 minutes or so, I'd like to talk to you about social robots and artificial intelligence. But first, let's have a look at some robots. So here's one social robot, Pepper, a rather tall, quite complex machine. Here's Vector, quite small, pretty much the same technologies, but shrunk in a very small tabletop package. Robots can be very cheap and cheerful, such as Keep On, which was a Christmas novelty for a few years. And they can be, of course, very expensive one-off devices, such as Android robots. And of course, I should mention Furhat as well. So what you see here is that we have lots of different technologies in lots of different packages, but they have one thing in common. And that is that all these robots can only sustain narrow interaction. And with the narrow interaction, I mean that the interaction between a person and the robot is quite constrained. Yeah, it's quite closed. And I was trying to think of a metaphor, and I think a row bridge is, a rather okay metaphor. So the interaction needs to get you to the other side of the river, and the interaction is narrow. Yeah, you need to stay on that bridge to get to the other side. The moment you step off, you kind of end up in the churning river of open-ended interaction, and that's not where you want to be. And even that bridge is, quite flaky. You could step through a branch there and failing speech recognition or so, and again, things fail miserably. And so the question really is, can we step outside those narrow interactions? Now, I don't want to say that narrow interactions are bad. They have a place in human-robot interaction, and we have beautiful applications where narrow interactions do exactly what we want them to do. So, for example, in education, or applications where we use the robot in care, in retail or entertainment, or in elder care, narrow interactions sometimes just work, and they're quite robust. So that's exactly what you want from those narrow interactions. But I think that what we really want is an open-ended interaction. This is kind of the dream, isn't it? But if you look at research in human-robot interaction, you're going to see that about half of research studies still use Wizard of Oz. So the robot is teleoperated by a human operator. Now that's fine for some applications. Sometimes you want to do a quick and dirty experiment, and then you're going to substitute the failing technology or the immature technology with a human pulling the levers. Natural language, for example, and it could be substituted by someone just banging away at the keyboard and speaking sentences through the robot. And sometimes Wizard of Oz is even entirely appropriate. So, for example, if you have a situation where you want to interview a child about potential abuse, and there's a therapist using the robot as a kind of a neutral mediator and just listening in through the robot and operating the robot, that's an entirely appropriate use of Wizard of Oz. But I think that Holy Grail for us is to build autonomous HRI, and certainly I know it is for me. I want these robots to be autonomous. But what we do know as well is that programming autonomous HRI, and certainly open-ended HRI, is incredibly difficult. So it's not only difficult, it's also very time-consuming. And these robots have limited scope. Yeah? So you can have a small conversation, and as soon as you kind of step outside the garden path that has been programmed, it fails, much to the annoyance of the user. The interactions are also not long-term. They're often even just a few minutes long. And commercial robots that have attempted open-ended interactions, such as Jibo or Vector, they fail. The customers who buy these robots don't think they get value for money. So can we move beyond that? Because there are new robots appearing all the time. Here's another commercial initiative, and the question is, how can we make sure that people are not underwhelmed by the interaction experience that they have? They desire open-ended interaction? How can we give it to them? Now, I don't really have the answer to that question, but let me propose that data-driven artificial intelligence is the way forward. Why? Well, first of all, hey, we've got all these beautiful tools now for machine learning. It would be a shame not to use it for HRI. But also because we want it. We want to have open-ended HRI, so we might as well use the latest tech to see how far we can get. Now, let me give you 3 examples of research that we have been doing. And the first one is on multimodal interaction. Now, think about chatbots. A chatbot is unimodal. It's a text interface with a piece of AI. You type a question and then it comes back with a written response. Now, the moment you put a chatbot on a robot, things start failing. And the reason is that the chatbot, a classic chatbot, doesn't have access to the external world in the way that people expect a robot to have access to the environment around it. A robot has cameras and microphones as shown by the eyes and the ears that the robot has. And so people expect the robot to be able to see them. So they might walk up to a robot, give the robot a little wave. And if the robot then doesn't respond, the interaction fails. So how can we build or kind of extend a chatbot that it becomes multimodal? Now, we scaled our ambition back a little and looked at how to start a conversation. Now, every conversation starts with a bit of small talk or phatic communication in the academic parlance. And it's this little question that doesn't really carry much meaning, but that serves as a kind of a verbal handshake. The, hello, how are you? Oh, dreadful weather. Or the best conversation starters actually refer to a visual feature of the people you're meeting. So for example, oh, that's a great shirt you've got there. Now, can we auto-generate these conversation starters? Now, the pipeline that we used first needed the data. And so what we did was we collected images of people looking into a camera. We went to Flickr for that, kind of filtered Flickr, and looked at, chose about 4,000 images of people looking into the camera. And then we gave these images to crowd workers and asked people to tell us or to give us 3 opening questions. Have you always had freckles? Were you born with red hair, etc., etc. Polite questions, we hope, that can lead to a friendly conversation. Now, we didn't want to kind of go straight from the image to conversation starter, so not end to end here, but instead we used a captioning network to kind of make the challenge a bit more feasible, because otherwise we would need too much data. So captioning networks do the following. They take an image, and off that image, they generate a number of small descriptions, textual descriptions of various elements in the image. And so starting from that textual description, we then try and generate a friendly opening question. We used generative neural models based on BART, so a variation of a transformer. We used retrieval models that just looked in the training data and selected the question in there that was probably most appropriate. So let's have a look at a video of some people meeting our robot.
Hi there. Where did you get your earrings? Hi there. Do you like wearing red? Hi there. Where did you get your glasses? Hi there. Where did you get that necklace?
So that seemed to work. Does it always work? No, it doesn't. If a male user with longer hair approaches our robot, it asks him about his lovely earrings, because it has learned the association between long hair and the user typically having earrings. So overgeneralizing, as in any machine learning application. But it does show the promise of a data-driven approach to slightly more open-ended interaction. Let's have a look at another example, co-speech gestures. So the gestures that people make when they're talking, such as I do too often. Can we auto-generate them? So there are many models out there. In the last few years, there's some really great research on using kind of training data, in this case TED Talks, and then use neural networks to generate these co-speech gestures. So you kind of provide the text, written text or audio, and then the model generates the hand gestures that go with it. So let's have a look at a video of that.
As you see, I can move my hands freely according to the speech. I can make gestures like holding my hands, widening hands, or describing abstract concepts.
So that's quite okay. It's a bit slow because the motors of the robot can't keep up with the speech, so they slow the speech down to match the motor speed. But how good is it really? Well, for that, we can look at a challenge that was run last year, where they compared a number of machine learning models against a baseline. The baseline was just a recording of an actor being played back on an avatar. And that's what you see there in the at the top. The dark green box is the baseline. And the orange boxes there are the performance of the machine learning models. So they're not, they're certainly lower in performance than the baseline, which is as expected. But have a look at this light green box. This is the baseline, but with mismatched audio. So it's the actor using co-speech gestures, but with the wrong audio file on the video. And even that is judged as being better than the machine learning models. So we're not quite there yet. Bridging that last gap to perfection turns out to be really challenging. And I think the main reason is that we are incredibly sensitive to small mistakes in social signals. Let me propose another machine learning method in which we learn action selection, so doing things, taking actions on the robot, but using a data-driven approach. So typically with robots, you would use reinforcement learning or learning from demonstration. But with social robotics, that is difficult to use. So we propose something different called SPARC, which stands for Supervised Progressively Autonomous Robot Competencies. And here you will be learning online from a human expert. So there's an expert controlling, teleoperating the robot, and the robot gradually takes over. The best way to explain it is to kind of compare it to autocomplete on a phone. If you buy a new phone, this phone doesn't know you at all. It doesn't know your name or the names of your friends or where you live. But as you use it for weeks, it gradually learns these tidbits of information. And when you're writing a message, it then auto-completes your sentences for you using the right information that wasn't in there at the start, but that it has learned as you use your phone. So the same thing we want to do with robots. So there's an expert controlling the robot using a tablet interface, and the robot is interacting with a user, a child here in this case. And so at the start, the effort that the expert needs to put in is quite high, but gradually the robot takes over and increases in autonomy while the effort is minimized. And we hope that at all times the performance of the robot stays high. I haven't got time to go into detail, but let me just show you one graph of an experiment where we used this to teach a robot to run through kind of a piece of teaching, so some educational task. And what we see here is that the robot really takes over the style of teaching from the human expert, which is brilliant. It's kind of exactly what we hope to see. Now, recently at the Bristol Robotics Lab, the same method was used to teach a robot on how to become a fitness instructor. So the robot is being teleoperated by a fitness instructor to get people to run 5 kilometers. And this graph kind of shows really nicely what the robot learns. So have a look at the right-hand bar on this graph. Yeah, so right there. These are the instructions given by the fitness instructor on that tablet interface. And then the middle bar of that graph shows what the robot has learned. So the behavior of the robot pretty much matches the behavior of the human expert 100%. So it has become a virtual copy of the human expert. Now, have a look at the left-hand bar. This is what the human expert thought the robot would have to do. So these are kind of heuristics that the human expert would program in the robot, and they're very different from what he actually did. And so it shows that people are very poor at explaining what the robot should do, and they're much better at demonstrating what a robot should do. So this method really might be a way forward in teaching robots on how to become social. So let me wrap up by arguing that social human-robot interaction is one of the biggest challenges, if not the biggest challenge that AI is facing. When we are having a social interaction, our entire brain lights up like a Christmas tree. Everything is active, your motor cognition, perception, language, memory, everything is involved in having a face-to-face social interaction. And it means that we need to replicate all these elements on a machine. And still, at this very moment, we don't really know how to do that. So not only is this a challenge that brings together the entire AI department, as some of my colleagues say, but it also will help us understand the human brain better. It'll help us have a model of how we do these things in as a uniquely social species. So I'll finish on this note, but not before thanking my colleagues who fed into all this work that I presented here. And I hope I'm online now to take a few questions. Thank you.